All right. Hello, everybody. Welcome. Welcome to the Path Seminar Series. And I'm delighted today to welcome Professor Rama Yedavalli. Professor Rama Yedavalli comes to us from Ohio State University, where he's had a distinguished career. He also has a business that he's founded called Robust Engineering Systems. And today's talk, he'll talk about stuff that kind of evolved from the lab to his company. But just some background on Professor Yedavalli. Has had a distinguished career over 3+ decades or so in aerospace and mechanical engineering, fellow of IEEE, ASME, AAAS, AI, AA. I also know Professor Yedavalli because he's been super involved in the ASME Dynamic Systems and Controls Division. In addition to this distinguished academic work, service and participation in the community. And I kind of grew up in this community. So Professor Yedavalli was one of the, very important figures. Many awards, one Hugo Shuck stuck out to me. Also, something I appreciate in just looking at your bio is just the commitment to mentoring of students, PhDs, postdocs, who have gone on to places like General Motors, Boeing, Pratt & Whitney. I think someone is at Cal State Long Beach.
Right.
Yeah, that's awesome. Coming to California. And Professor Yedavalli has spent some time here at Berkeley. Was talking about how he did a sabbatical around the 2015 timeframe, hosted by Path faculty, including Carl Hedrick at the time, and then Professor Roberto Horowitz. But also, Professor Rama Yedavalli is famous around these parts because of his son, Pavan Yedavalli, who graduated with a PhD in urban computing, working with Paul Waddell. So apparently, when Professor Yedavalli walks the halls, they say, "You're Pavan's dad," which I love. So, and delighted to have you today and to talk about, I won't steal your thunder, just to talk about controls and linear systems and the concept of eigenvalues. And I think is maybe going to give us a new perspective on how eigenvalues are useful and maybe they're misleading. So some of the things you might learn in class might get turned upside down a little bit.
Well, we'll see.
And so I think this should be a very intriguing discussion. Thank you so much for coming.
Thank you so much, Scott. Again, I really appreciate you inviting me. It is a very big platform for publicizing my new research results. Again, thank you so much to give me the opportunity to share my excitement about these new results. Again, thanks also for your kind introduction. I simply believe that being active in research and then surrounded by like-minded people like you keeps me fit and happy. So that's why I keep doing this. And then I hope some of these new research we are going to talk about, which may sound a little so-called controversial, but is again knowledge-based expansion. So hopefully we can learn from each other. In a way, I learned a lot from other non-engineering fields like ecology. So that's what I'll try to kind of discuss a little bit in more detail. But again, without much ado, let me kind of start. Another small thing I want to say here is, in a way, I'm kind of a little feeling unusual because, as you can see, the title of the talk, I am acting more like an entrepreneur for today rather than as a professor at Ohio State University, which is kind of strange even for me. But it turns out that some of the research we have done in the last, maybe I should say, 2015, so it's the last 6-7 years. I turned things upside down and I learned a lot from this ecology research and was trying to help out our engineering field by the knowledge I gained from ecology. But in the end, it turns out that there are some things we can learn from other fields. So my only message would be to keep open mind with all the other disciplines. Appreciate what others are doing. Maybe some of the things we have been doing, maybe they can be done better, maybe. So by embracing those new ideas. So let us have an open mind. So it's not a question of controversy, it is a question of learning more about eigenvalues. Maybe let us put it that way. So in some sense, I will be talking also more like an entrepreneur because I will keep saying my firm or our firm, robust engineering systems, found out this, found out that, even though obviously I'm blessed to hold a academic professor title at Ohio State University. And maybe I should also kind of formally thank Ohio State for believing in me and keeping me active like this. So the small, again, kind of subtle detail I need to mention at the advice of my IP attorney is that, yeah, while everything looks exciting, but please kind of don't use it yet completely without getting some kind of the IP protection honored. And
we'll pay you royalties.
Yeah. So
we'll pay you the royalties.
That's right. Yeah. I'm now looking for some money. As an emeritus professor, I don't earn anything, you see. So I better earn something through my
Maybe.
Okay, so let me kind of hopefully I will try to cover as much as I can. But I do have to, because I'm talking like an entrepreneur right now. I should say that we supported the last conference, American Control Conference is our flagship controls conference. So Robust Engineering Systems is proud to have been a brand sponsor. So in that sense, some of our controls community, now I should also add, because of the new results, signal processing community also. So I'm not talking only about control system design, but I'm also talking about signal processing, which is related to sampling and other signal conditioning ideas. So again, I appreciate it if you simply go to our website, that is www.robustengysys.com, and kind of see what are the new kind of concepts we introduce as a company, which is of course offshoot of my professorial activities, but learning from the ecology. So I will now, from now on, I'll keep calling my results as robust engineering systems, control systems, and signal processing toolbox. So think of it as the product. That is the product. That's it. And some of the new words you will think about today will be transformation analytic approach. Is it pointing something here? Oops. Is there any pointer that the one that shows here?
Yes, but it might not appear on the screen.
On the screen, I see. Okay.
Yeah.
Okay, no problem. So yeah, some of the
You're
new words.
welcome to stand up and point.
That's right. Yeah. Some of the new words. I will understand. Yeah. Some of the new words you will think of. You'll see the so-called transformation allergic approach. That is something I coined, obviously. And then the reason it sounds kind of controversial is that everything we learned in our undergrad books and graduate level books on control theory, linear algebra, matrix theory, I'm allergic to all of those. Phase variable allergy. I'm not using phase variable. We use phase variable so much, but I'm not using them. Mapping theorem allergy. Everybody kind of assumes that mapping theorem is all very good. Interior of the unit circle maps into the left half of the complex plane. Not really. Not really. So mapping theorem allergy. Tailored A power 0. If you go to MATLAB and give any matrix, just a standard real matrix, any order, anything, and then ask it, what is that matrix power 0, A power 0, which comes up, by the way, why is A power 0 that important? It comes as the last term in the Gable-Hamilton theorem. A power and something C1, A power, and then the last term is A power 0, which is they put as identity. Determinant coefficient is multiplying the identity matrix. So therefore, A power 0 is taken as identity. But it is taken as identity for any matrix. We are saying no, it should be tailored. A power 0 should be tailored to the element of structure, the sign and magnitude structure of the A matrix. Not everybody, every A matrix can have A power 0 as identity. And then, of course, so the final important word is convex stability. Therefore, the only way I can, RES can simply differentiate between current literature methods is that we know about Hurwitz stability, we know about Schur stability, we know about sample data, discrete time system stability. Okay, so then what is that you are talking about? And let us call it. Hopefully, people will call it Yedavalli stability. That's a different name, but I hope not. But convex stability. So that is the new word I want to use. That is the kind of so-called new way of real estate variable convergence, convex stability. Okay. So within the limited time I have, there's so much to cover, but obviously so I'll try to be as precise as possible, but excuse me if I run out. I'll go through some slides very fast. Okay, I have a quick, the reason suddenly all of this became allergic is that we don't have to do it like that. So therefore, right from the beginning, I will talk about we simply have a matrix A, and that could be a static system, linear algebraic equations, Ax equal to Y. So there also A matrix is there. So more emphasis on A matrix as how it is used is the next matter. So dynamic systems and static systems. And then we getting from the kind of the reviews we got for the papers and all that, and all the kind of so-called in a way I should say dialogue we had many conference papers are submitted, is that not many people are familiar with our with the so-called qualitative size stability. Again, maybe for some of you, hopefully, it may be the first time you are hearing about it. But I want to kind of tell you that that's an amazing concept, but devised by ecology people. So therefore, qualitative size stability. The word qualitative is important. Therefore, in a way, it is something like almost like a tussle between quantitative people and qualitative people. Qualitative sometimes wins. So therefore, that's what it is. Then I'll quickly go through that. So why suddenly in the last 7 years I became such kind of allergic to eigenvalues, allergic to phase variable? Why? Is that I got it? I mean, as a professor, before I got my eyes kind of open to ecology research, I myself was writing textbooks like this on robust control, and this is Springer. So I was kind of using all our TC methods or all our linear algebra methods, undergraduate text flight dynamics control, where we used all our eigenvalue results just like that, without any question, without any. So suddenly, why did I become like that? The reason is that juxtaposing, I will call all our linear algebra methods, including my books there, transformation compliant methods, TC, which transform from one system to another system just by a non-singular transformation. And we just do it just like that anytime. So the reason, therefore, when I put my TC methods with our QLSS methods, that in ecology, when I put them together, there are some things kind of not correct here. So therefore, some of the unattractive properties of eigenvalues. So therefore, that is the big story. Therefore, eigenvalues we routinely use eigenvalues. To be very frank with you, you give a matrix to an undergrad, go MATLAB, IGFA, negative real product, astray. No. So eigenvalues are so embedded in our kind of mindset, is that when I'm saying eigenvalues don't have that many good properties. But that's and it has gone into such a kind of an extent that once I learned things from QLSS theory, I was able to produce counterexample to every one of the theorems I see in the Noble and Daniel book. Suddenly, surprisingly, counterexamples. So therefore, then I said, okay, convex stability is a very kind of strong and important new concept. So let me publicize it and let us learn from it. So convex stability. Therefore, if I'm hating, like so-called allergic to eigenvalues and don't like their properties, then what are you doing? I am saying, let us devise some other state variable convergence measures, which I'm now calling them convex stability indices. What are convex stability indices? We'll talk about it, we'll see. But so don't use eigenvalues, use convex stability indices, and let us see what the advantages are. Okay, so that's again when Scott was kind enough to invite me to give a seminar, especially here in PAC. I realized that maybe I should introduce myself, even though Scott gave a nice introduction. Just to quickly, the reason I flash this slide is to simply let you know that yeah, we kind of have been supported by a lot of funding agencies and all that. So therefore, this new knowledge hopefully will make them realize. These are the two books. I'm kind of very proud of this and very happy. It took a lot of time to. This is an undergraduate level flight dynamics and control book. For my own OSU students, I started, but fortunately, that good. I spent a lot of time in my other alma mater. My first alma mater, India is IISc Bangalore. Purdue is my US alma mater. So I spent a lot of time at IISc to write these books and all that. So I'm happy about all these things. Yeah, so the third book, I have actually a contract with Yedavalli. They are kind enough to wait until 2025. So now I think I get a chance to talk about this convex stability, hopefully in that book, and then that should be good. One other small thing I want to say is, yeah, so why is that suddenly this much of kind of entrepreneurial spirit for my new toolbox? Just like eigenvalues have been used and then MATLAB routines are used routinely for many, many engineering applications. Exactly the same thing can happen here also, nothing different. All our control systems ideas can be applied to all these different engineering systems. And in fact, even non-engineering systems, biomedical, and if we actually work towards it, we could use some of these ideas in biomedical and medicine. As I said right from the beginning, the very reason this is multidisciplinary and interdisciplinary is that, right? This ecology is what gave me these new ideas. So with the little time I have, I would rather first kind of impress upon you the unique features of this toolbox. And then if we have time, why is it like that? Why is it like that? Then we can figure out. So let me first simply say, how is my toolbox different from, maybe I should say, a MATLAB toolbox actually. So is the only software that completely addresses the matrix stability. Yeah. See, when I was doing my robust control research, Bob Barmish from Wisconsin used it to give, every time we came up with some method, Bob Barmish used it to give a counterexample to that. Every time. Yeah. So this is the only kind of a toolbox where I learned from those counterexamples Bob Barbish used to give, and then why those is happening, why that? So it turns out that all of those counterexamples were due to the unattractive properties of eigenvalues and our blind belief in eigenvalues. We used to believe that is, and then when a counterexample was there, maybe I asked if everything to do with the eigenvalue. So this toolbox I learned from robust everything is the only one which really addresses as to why all those counterexamples used to be there in our robust control literature. Then, so static output feedback stabilization. Everyone in the controls community knows that every survey article, static output feedback stabilization is the most tough problem to be solved. Till now it hasn't been solved. Well, once we come out of the eigenvalue, so-called maybe yeah, then suddenly our static output feedback stabilization was solvable very easily. So therefore, again, all these days we were not able to solve static output feedback stabilization because of eigenvalue. We used to say always use eigenvalues, but the moment we came out of eigenvalues, we were able to solve it. And this could be of interest to all of us here in the room also. So what is convex stability doing? It is suddenly reducing the computational complexity because we are not solving actually something equal to zero. No, we are not finding the roots of anything. Yeah, we don't need to. So therefore, suddenly there was a lot of computation savings. How does it help? Why? I think if we can do some research on that, I can bet my books that it will imply that for all these energy constrained systems, if we put no burden on the computation, most of its energy is wasted in the unnecessary computation. I'm sure that we can somehow see that it will be imply longer life. Maybe your batteries will last longer instead of lasting 4 hours. Maybe if I want to do some small addition multiplication type of solving a Riccati equation and all that, maybe it will say it will last for 10 hours. So therefore, that is something happening there. And they are applicable to not only continuous time systems and dynamic systems, but also to discrete time and sample data. Yeah, that's important. All these years we have been kind of taught and we dealt with the notion that Hurwitz stability, Schur stability, sample data, they're all connected with each other and they all start from the Hurwitz stability. No, they're all different. They're all different. One may not imply the other, as we shall see in a minute. Now, Hurwitz stability and Schur stability may not coexist at all if the matrix is like that. So we'll see. Then finally, so why is that? If people don't believe, so I mean, let me say, there was a lot of resistance to accept this, by the way, for the last 5 years, 6 years. So finally, yeah, we'll see how it prevails. But the point is that so the least our convex stability can do in this new toolbox is that okay, MATLAB design you keep on doing MATLAB design, but suppose there is an unstabilizable, undetectable, unobservable, uncontrollable system, then you kind of say, yeah, we can't do anything. No, give it to me. I will stabilize. So therefore, the least, I mean the best, and what should I say, least or best? Yeah, even if we don't keep on want to using eigenvalues, but in that case, all those problems you are not able to solve, give it to me, so-called non-uniform, we can solve it. But with a so-called distributed actuation and sensing. So yeah, I don't know whether we'll get a chance to elaborate on it, but yeah. So all those so-called uncontrollable, unobservable, unstabilizable, undetectable systems can be easily solved if only we introduce the notion of distributed actuation and distributed sensing. I also want to kind of point out that I read some papers on the medicine-related journals. They are talking about what do they call soft actuators and soft sensors. I think they are related to this one. So I just want you to keep that in mind. So at the risk of sounding boastful or to kind of, no, actually not boastful, to kind of convince you that I'm not the only one excited about this one. One third-party technology consulting company, OSU sent my invention to, without my knowing, they sent it to a company. They came out with an invention report saying that, oh my God, this thing will definitely positively disrupt chemical control. That is what they said. I'm not saying. And then finally, so therefore, in other words, I have earned the right to kind of, in a way, sell you a new toolbox, which has definitely some attractive features. All right. Then if I'm saying this now in 2025 March, what happened? So fortunately, I had a lot of trouble convincing people. Some of the reviews were very caustic because I'm going against the grain. But in the end, once I was persistent, I was never discouraged by negative reviews at all. Instead, it actually made me come up with those counterexamples they wanted right away. Then they will be saying, there's nothing they can say now. I gave a counterexample to Hamilton. I gave a counterexample to Claude Scientific. I gave a counterexample to Liav matrix equation. Then what can they say? So therefore, all of these are actually in the public domain, but they are IP protection. So therefore, the so-called static output feedback stabilization for a special case of null plant matrix appeared in last year TACC. And now I'm actually working on the general case. This is a very special case, but for the general, we'll talk. Okay, so first of all, what is this so-called convex stability? What do I mean by that? What is this transformation allergy? So when I say transformation allergy, therefore I'm given a matrix. We TC now I'm calling TC guys, transformation compliant guys, including me. We simply keep on transforming from one system to another system. Do keep on doing that. When I say transformation allergy, no, I don't want to transform them. You gave me that particular matrix. You want to stabilize that system with that one. So therefore, in a way, I'm not. Somebody tied my hands not to do any transformation. Can you give a condition that particular A matrix, that particular will it stabilize or not? Is it stable or not? Okay. So therefore, my elements are free in the. I'm sorry. Yeah. Okay, next step. So it is a concept of nested stability. What is convex stability? If I have an nth order matrix, say sixth order, the fifth order, its convex stability is dependent on the fifth order, but the fifth order is dependent on the fourth order. Like that, you go until the smallest matrix is the simple second order system. Therefore, a simple second order system's convex stability affects the convex stability of all the other higher order ones, vice versa. All the higher order convex stabilities are dependent on the simple second order system. Therefore, they are connected. Did we do that in TC methods? No. The fourth order matrix, every order matrix has the same negative real part eigenvalue effect. So therefore, there's a big difference between convex stability and this. Real state variable convergence. I will keep on using the word. I will not even use the word stability because stability means, so many stabilities, definitions. Heavy stability, should stability, convex stability now. So better to call real state variable convergence. You gave me x dot equals AX. Well, not even x dot. What about algebra? You gave me AX equal to Y. Does there exist a x for the given Y? So therefore, strictly speaking, we are talking about matrix theory here. Not even ordinary differential equations, not even partial differential. No, not differential matrix theory. So AX equal to Y to be a static system. Continuous time dynamic system, ACTD, continuous time dynamic system. So take out that Y and put X dot, then it becomes a dynamic system, differential equation. Take out that Y and put XK plus 1 XK. So discrete time dynamic system. Forward step, backward step. Then our famous exponential matrix. The sample data system actually takes the continuous time system A and then puts A to e power AT. So therefore, this is, and then there's a constant sampling period T. What if that constant sampling period T happens to be unity? So I actually coined a new, I never saw that word in any of the sample data system. Unit second sampling period, unit second sample data. What about if the T is equal? So it turns out that numeral 1 is causing havoc among all them. How do you identify phase variable? X1 dot is equal to X2, X2 dot is equal to X3, etc. So the X1 dot, that one there, X1 dot equal to X2. That one you see on the companion matrix. That's this causing a lot of havoc. So therefore, numeral 1 is kind of that is just like numeral 0, numeral 1 is also. So everything between 0 and 1 have a single okay. So therefore, what is the purpose of this slide? So first of all, before jumping into Hurwitz stability, no, we are talking about a matrix, a real square matrix. It could be used in so many different ways. So you tell me what purpose it is being used, then I will tell you what the condition for that. Therefore, different. So different forms of that A matrix where it is used, that is TC. What about when we are discussing that? why didn't we talk about the same A matrix? What if it doesn't have any magnitude? It only has signs. That's what QLSS people are doing. So that means I take the sign pattern of the matrix. Second order matrix has, there are how many entries are there in second order matrix? 4 entries. So each one takes 0 plus minus signs, 3 signs. So 2 to the power of 3 to the power of 4. So 81 sign patterns are there. So in those 81 sign patterns, I can put and the non-zero signs, plus minus sign, I can put some magnitudes there. So therefore, there are so many matrices. Now, a simple fourth order matrix has 43,064,721 sign patterns. 43 million in a fourth order matrix. So I can actually put magnitudes, leaving out the zeros. Zeros are zeros. So in that case, I have an enormous number of matrices cropping up. We never considered that. TC methods are constrained. They are looking at only a very small subset of so many matrices possible. And then I will call them quantitative sign matrices. What do I mean by that? You take a sign matrix, but put magnitudes in the non-zero sign entries. Then that is a quantitative sign matrix. That's one. Therefore, quantitative sign matrices are actually a subset of qualitative sign stable matrices. Therefore, nobody talks about that much in our TC community. Another kind of oversight I saw in our TC methods is that we ourselves said any matrix, any real square matrix can be described as A sim plus S Q sim, where A sim is A plus A transpose over to S Q sim is A minus A transpose. So when we see that A sim is highly related to A and S Q is related, so all these three matrices are extremely intricately related to each other. So then why is that Herbert stability is giving a condition for state variable convergence only on A? Nothing is said about A sim and S Q. Negative real part eigenvalues of matrix A. Why? No. These A matrix X are also real state variables. A sim matrix are also real state variables. SQ sim matrix, actually they are also actually real variables. Our TC methods are thinking that they are pure imaginary. So actually there are, if there are n state variables for A in the dynamic case, n real state variables here, another n real state variables here, another n real state variables. 3 n real state variables are there, right? So we have to promise convergence of all those 3 n real state variables, not just the original X. That's a big revelation. So, and why so much importance given to ASIM and SQ? Because again, you only told me, Noble and Daniel's book told me that every matrix, a real matrix, square matrix, has a field of values. What is that field of values? So I couldn't write a diagram, otherwise I should have put a diagram here. It would have been easier to see as a diagram. But with some lack of time, we have my kind of PowerPoint presentation skills, lack of that. I simply put it in a conceptual way. So you all know about it, right? So we have a eigenvalue ellipse. So a rectangular bounding rectangle is always there. What is that bounding rectangle? The symmetric part eigenvalues, the maximum of that on the negative side, the maximum of that on the positive side, that will give you the bounds on the eigenvalues of original A, but they are the bounds. Similarly, on the imaginary axis, the skew symmetric matrix eigenvalues will give the maximum frequency plus side minus. So that therefore, when the field of value theorem is giving so much importance to A eigenvalues, A sim eigenvalues, SQ sim eigenvalues, why are you neglecting all that information? Why are you neglecting all that? So That means A sim real eigenvalues is telling you something about A. ASQ sim eigenvalues and frequencies are saying something about A. So therefore, AS eigenvalues are very much linked to A sim eigenvalues and ASQ sim eigenvalues. So therefore, therefore, this triple, you cannot separate them out. Our TC methods are looking at A matrix independent of A sim and ASQ. No, they're all related, extremely intricate. The triple is together. It's like a family. In fact, these are so close. You cannot separate them out. So why? Why? Because again, our QLSS people said, hey guys, signs are important. Yeah. If you look at the asim matrix, can you tell me what is the how a symmetric matrix look like? Aij is equal to Aji. So if that is plus, this also is plus. If that is minus, this is also minus. So there's a sign pattern related constraint in the sim matrix. Same thing with SQ symmetric. How does it look like? Plus sign there, negative sign there. Predator pressure. Beautiful names. When you look at the QLS jargon, it's so beautiful and so conceptually clear. And therefore, anyway, the point here is that we have to kind of, both of them are. So therefore, QLSS methods are not alien to our TC methods. No, they're part of it. We just do not care about it. That's all. Yeah. So therefore, then I made another small ploy on that by knowing that after it. Then I said, okay, A is equal to A sim plus A skew. That is our TC people had said our textbooks. But I said, okay, let me try another, knowing from realism. I am saying that every real square matrix can always be decomposed into three components. A main diagonal, a main anti-diagonal, right? Like that. And then everything in between. Interconnections. That's the beautiful word they use in ecology. Interconnections. Interactions, interconnections. So therefore, every real square matrix can be decomposed into three. If that is the case, when you say A square, what should happen? AMD square, AMNTD square, AICD square, and the products of those. Did we ever consider that? A squared is simply A times A. Nobody cared about this, that commutativity constraint. That's what I'm saying. In the retrospect, when I bring out all the TC textbooks are violating their own stated theorems. They only said AB is not equal to BJ. Then why are you not implementing that here? When I take A square, I get an A and B times AM MNTD product. Why are you neglecting? You always said AB is not equal to BJ. So AMD times AMD is not same as AMNTD times AMD. AB is not equal to BJ. You always said that. Why are you not doing implementing? Not getting implemented. So therefore, there's so many. That's what I mean. When they're juxtaposed, then so many silly things are happening in the DC method. They are violating their own sayings, statements. Yeah. So therefore, if I simply say real square matrix, I can think of it so many ways like that. And why this is important? So without constraining, I can put my AMT elements here or here. So I can play with those elements and signs anywhere I want. They can be freely fabricated. So how did I get all those counterexamples suddenly? I can fabricate. I can fool the easy method to fabricate a matrix that will have eigenvalues variant under linear transformations. So we said eigenvalues are invariant under linear non-singular transformation. No, they are variant. I can build a matrix. That's what I did. I built a matrix, a user fabricated A matrix, and a user fabricated linear non-singular transformation matrix, D inverse AZ. G inverse AZ eigenvalues are not same as eigenvalues of A. You said they should be same. No, they are not. Simple. I built a user fabricated A user fabricated Z inverse AZ. According to TC methods, they are supposed to be the same. eigenvalues are invariant under linear non-zero transform. Now, that's it. That itself is. And then it took a lot of time to convince people until I gave them hard counterexamples. But it took that much effort to give those. And we underestimate 2 by 2 matrices. Everybody thinks in TC methods. 2 by 2 matrices are 2 by 2 matrices are very simple, nothing. No, it is a 2 by 2 matrix, which is extremely critical. Yeah. So, because as I told you, convex stability connects all of them together. 2 by 2 to 100 by 100, 100 by 100 to 2 by 2. So therefore, 2 by 2 is not easy matrix. Finally, in fact, yeah, maybe it is better to kind of skip to. I have hundreds, a lot of slides, but I think the main points, yeah, there. So, yeah, one other small thing. Main diagonal elements are actually residing on the real axis of the complex sphere. Real axis, imaginary axis. So main diagonal elements are residing on the real axis, and main anti-diagonal is residing on the imaginary. If you can see like that, things will be extremely simple. Extremely simple. And one other small oversight, I think I would say costly oversight, is for a fourth order matrix, I to the power of 4 is 1. But in other words, I omega to the power of 4 is 1 when omega is 1. We forgot, we neglected it, or it is an oversight. That never was used. So, and then how our eigenvalue is calculated? Determinant of lambda I minus a equal to 0. Why only I there? I means it is giving importance only to the main diagonal. What about my main? So that's what I said in that other paper. X matrix cannot have its power 0 as simply identity matrix. It should be X. An X matrix power 0 should be X identity matrix. It cannot be normal identity matrix. Lift it up. A omnivorous matrix. That means if the matrix has no zero signs at all, everything is all plus minus everywhere, then its power 0 cannot be identity matrix. It has to be unity matrix, all ones. Nothing big deal actually in retrospect. Yeah, in retrospect. Another thing that because 2 by 2 matrix was simply taken as something like a toddler matrix, no big deal. No, 2 by 2 matrix is very big deal because I omega squared is -1 at omega equal to 1. Why that was missed? Because our MATLAB routines, they take a real number as a special case of a complex number with imaginary part 0. They said omega is. When sigma plus j plus or minus j omega. When omega is 0, is real. No, that's wrong. Omega can never be 0 actually. Omega has to be, just like sigma is something, all numbers, omega is also all numbers. No, not just 0. So what does that mean? It means that TC methods, their overemphasis on, determinant has to be 0. If determinant is 0, it's not invertible. So what? If determinant doesn't have to be, negative, it doesn't have to be non-singular all the time. Every matrix doesn't have to be non-singular. Let it be singular. What is that? If it is a singular matrix, the MATLAB command gives condition number infinity. Why? All 0 matrix is a well-behaved. It's all zeros. What is wrong with that? It's not invertible. Why should it be? Why should it be planned it as a ill-conditioned matrix? It's not ill-conditioned. For a QLS fellow, why are you talking all my 0 matrix as something like an outlier or bad thing? No, you will be well conditioned. It's a low condition. Therefore, yes. Therefore, what is kind of an amazing thing? So Why are we making zero as a very complicated number and then in the machine precision? What is a real zero in a computer? E power minus 235. No, not necessary. I can say zero is 1 minus 1 is 0. I power 4 plus I squared is 0. Pure real zero. I don't have any e power minus 235 machine precision needed for that. What does that mean? If you give me any matrix with all zeros and anything, take out the zero and put I power 4 plus I squared. If it is an even order matrix. Take out that matrix and put I power 5 plus I cube. Is 0. So that means any real matrix in our Noble and Daniel book, you are seeing that as a real matrix, but I always see that as an omnivorous imaginary matrix. Isn't it? I can see that as an omnivorous imaginary matrix. Because once I replace 0 to be I power 4 plus I squared, I see that as and then an omnivorous imaginary matrix, its power 0 can never be identity. And not only that, because the imaginary matrix, there's no need or constraint for the conjugate to be plus or minus. Only real matrices have that constraint, but not for. Once it is all pure imaginary complex matrix, imaginary is complex. So then there's no need for a conjugate. That's why right at the 2 by 2 matrix level, our MATLAB routines made a mistake and saying that, that the mistake was right in the 2 by 2 matrix, and that 2 by 2 matrix eigenvalues propagated to 3 by 3, 4 by 4, and all that, and 3, 4. So that is 4. Okay. So do I have another?
You think you can finish in 4 minutes? 4 minutes.
Okay. Right. Yeah. So therefore, I think that's good. Right. That's omnibus. So that's one final thing. Yeah. So once we accept that every A matrix has to be represented, not can be represented as A sim plus S, has to be represented as A sim plus SQ, then look at the beautiful, Rama, very interesting, we never bothered. I add that one 2A, this 2 is important. 2A matrix is in the first quadrant. Surprisingly, A plus A sim minus SQ is A sim. So this is a simply, and A minus A sim is a 0. So therefore the entire third quadrant is a 0, open third quadrant. Therefore, I am calling this is my most gratifying revelation. Means RES came up with 4th quadrant viewpoint of a complex of a matrix. 4th point viewpoint of a complex matrix. You cannot deny this. Noble and Daniel, anybody cannot deny this. You only told me. All of this is something you told me, Noble and Daniel. Any linear algebra book. I didn't do anything wrong. I just looked at it in a different way. In other words, what does it mean? This 0, why should it be only belonging to real axis? It can belong to imaginary axis. Therefore, pure 0, origin of the complex plane, has to be represented, all the 4th quadrant. Minus 0, I, plus 0, I, minus 0, plus ji. I mean that. So therefore, origin of a complex plane has to be represented by 4th quadrant. It cannot be represented by 2 halves, either left half, right half, or northern half, southern half. No, it has to be 4 quadrants. Nothing wrong. So this is what finally clinched my issue. Everybody said that's mapping theorem is it. So what happened was, the more and more I came about this so-called illogical kind of argument, I went back to Noble's, right in page 13. I said, that is what the mistake was. They said, definition 1.8, a real matrix is a matrix whose elements are all real. Okay. A complex matrix has elements that may be complex, okay? An imaginary matrix, here, an imaginary matrix has all elements that are all imaginary or all zero. There you go, gone. Your argument is gone. You are kind of putting a dagger in your own body. You only said A is equal to S plus SQ. So how can you make SQ suddenly zero in between the game? You change your roles in between the game. No, not again. Either you stick to that one, or so therefore, this entire left half plane is all zero matrix. Open. The matrix elements are only on the axis. The open quadrants are all zero. So how can you say a unit circle interior is transforming to entire left half of the complex plane? That's pure nonsense. I'm sorry for my. Doesn't make sense to me. Doesn't make sense to me at all. So therefore, with the time we have, let me skip some of these that I'm simply kind of saying that we simply forgot to emphasize this point. We wrote textbooks like this. Then this is, I already said that. So actually the very first dissatisfaction with eigenvalues came to me when Bob Barmish gave those counterexamples. Look at Bob Barmish's counterexample. I used to struggle with my robust. How can I say everything inside is stable interval matrix? Look at these four vertex matrices. They all have negative real part eigenvalues. Then Bob Barbish came up and said, Rama, no, I found an example where the interior matrices do not have negative real part eigenvalues. Oh my God.
What are we looking at?
We are looking at a family of matrices where the A11 element and A44 element are varying with an upper and lower bound.
Mm-hmm.
Two parameters varying in upper and lower bound. Therefore, four vertex matrices.
Yeah.
So at those vertices, all the four vertex matrices have negative real part eigenvalue.
Mm-hmm.
Then the question is the entire family having negative real part eigenvalues?
Mm-hmm.
The answer is no. At some point of A11 within this range, and at some point of A44 within this range, a bar is shown me here.
Okay.
So this is actually the starting point 10 years back battle between me and Barbish. Therefore, now after 10 years, I emailed Barbish. Baba, now I know why the heck this is happening only in a fourth order way. It is happening only in a fourth order way. Why? That I to the power of 4 omega squared. Omega was 1. I to the power of 4 was 1. So Counterexamples can never equate it to 0 at all. Something is 1 on the left hand side all the time. How can you equate it to 0? There is no eigenvalue. That is the culprit. It took many years. So this dissatisfaction with the eigenvalue started with this counterexample that Barmish 10 years. Nobody knew why this happened. Shankar Bhattacharya, explained, we were struggling to explain why this happened. Nobody knew. Why? We believed blindly in eigenvalue. We did not want to disturb the eigenvalue.
Do you mind giving concluding remarks, and then we'll take a couple questions?
So this project is stability. So that's no problem. And again, when you go through this one slowly, so two extremes. Therefore, one small kind of thing is, therefore, imagine that TC methods are pure, always concerned about the numerical quantitative. QLSS methods, I'm not saying they are gods either. They always talk about only predator-prey models, only predator-prey. So both of them have their own weaknesses. So therefore, therefore, the conclusion is that, what our RES CSSP toolbox has done is to put them together, and it's a very clever, so-called, I should say, combination of judicious mix of both of those extremes, I came up with our own kind of comments. Yeah, therefore that. Yeah, please go through that one. I clearly point out why I was dissatisfied with one other small thing. Maybe instead of kind of in a way talking in a negative way about eigenvalues, it was not their fault, I should say, actually, in retrospect. It was there in 100 years. 1905 was the Rauschenberg again. But our qualitative one came only in 1973. So therefore, it's okay to say that, oh, we were not aware of it at that time. So therefore, I was fortunate that in these 30 years, we saw that there's another viewpoint. Therefore, we took advantage. Therefore, that's how we can simply say. So therefore, in summary, eigenvalue methods are, think of them as single quadrant methods. Think of a convex stability as 4 quadrant method, as simple. So therefore, yeah, again, I gave, I just like they gave a sign matrix being always having negative part eigenvalue. Then I said, okay, I can give a matrix which is always non-negative real part. It is instability is independent of magnitude. So therefore, yeah, go through this. I know it is kind of still there, but please go through the detail of the slides. But I will conclude with the So therefore, then again, as I said, how come we were not able to solve static output feedback stabilization problem? Because by avoiding the use of eigenvalues, and I'm not going to come up with the general plant matrix. I have all the ammunition for that. So therefore, that's another thing. Okay, final. This is the final. So the major advantage of convex stability is that they do not lead to saturation effects because the gain is not linked to eigenvalues. Therefore, if I use a high gain, it is for some other purpose. In fact, the higher the gain in the static output feedback stabilization round or convex stability, the more robust it becomes. So convex stability does not need determinant, does not need eigenvalues. So therefore, this is the final. Again, pardon me for being a little kind of over enthusiastic, but it is like saying, recently we saw that deep set is doing something very fast compared to the other one. Why? Yeah, that unnecessary extra precision. Just like, so I'm saying you don't need determinant at all. Trace is enough. You don't need the determinant to say whether all the real state variables are convergent. So therefore, you don't need the determinant, and therefore you don't need that value set. So therefore, I want to collaborate with you, right, guys, and look for opportunities to collaborate. And I appreciate the advantages of this toolbox, and please publicize it. And let us do something together. More than publicizing, let us do something together. And by the way, later on, I went to Wikipedia and saw Jack Little, MATLAB owner. He sold first kind of code to MIT for a few dollars, and then became famous like that. And that MATLAB, now you see the $1 billion. So like that, I would love to sell it to you for a small price, but it's IP protected. So at least I need my patent money back. Yeah, but we should do something together.
Great. Thank you so much.
Thank you so much.
Okay. If
yeah, I know.
Of course, folks feel welcome to leave because we're out of time. But if anyone wants to ask a question, we can stick on.
Yeah, feel free to email me. The addresses are there. Even my OSC address should be okay. Yedavalli.1@OSC.edu, which Scott can share with you. Either way, I'll be happy to answer any questions you have. Go through the entire slide information. I'm sure you'll have some questions, and we'll be happy to work together.